let's hit a harder one, which is this initial value and final value theorem. The initial value theorem, and similarly the final value theorem, which from now on I'll just say IVT and FVT, refers to a really common question. The problem is that you're given some sort of Laplace transform. Just to make this a concrete problem, I'll say this one. And you're asked to find its time domain value at f equals t of 0, or its time domain value at after a really long time, after infinity. So here's your initial value, and here your final value. So it's not just as simple as plugging in 0 or infinity into f of s, because this is a frequency domain thing. The only way that you know so far, the bad way, to solve this thing is to transform f of s into f of t, which will take you a long time, and then substitute in t equals 0 and t equals infinity. And it's a bad way to do it because it's so hard to do this inverse transform. But the good way is to use IVT and FVT. And let's just start off with FVT. The final value theorem says that the value of the time domain function at time equals infinity. In fact, I'm going to make that explicit here by saying at time equals infinity is equal to the limit as s goes to 0 of s times f of s. And this way you do not need to do an inverse transform. So a couple of things to realize. The first is that you're multiplying by s. And the second thing is that when you want to make it infinity, you plug in 0 for s. And let me give a quick example. In the problem that I've given, up on top, the final value theorem says it will be the limit as s goes to 0 of s times s plus 1 over s plus 2 times s. So these s's cancel, and we are left with the limit as s goes to 0 of s plus 1 over s plus 2, and that's just 1/2. You can plug in the s equals 0 directly and you don't get anything unusual. That is a whole lot easier than trying to find the inverse transform of this. We haven't yet talked about how to take the inverse transform of this polynomial, but I'll tell you, it would take you about 5 minutes to do.
So you could just do regular laws of limits, like if you use transform, you just do third the numerator over the derivative denominator, do that. Or
Your audio is breaking up, but I think you're asking how do we take the limit, and the answer is the way to take the limit is to just try, and as far as electrical engineering goes, just try to plug in the value, and if it evaluates correctly, great, you're done. If it doesn't evaluate correctly, then you're going to have to do a little bit of algebra.
Yes, sir. I know. Sorry, I can hear me. I know how to take the limit. I was just asking if all the regular rules of limits apply, such as like L'Hopital's rule, things like that.
Absolutely. We're going to do L'Hopital's in the next example. but we're going to do a faster, easier way than L'Hopital's. And we're going to see this problem for f of 0, for f of time equals 0. So that's going to be the limit as s goes to infinity of s times s plus 1 over s plus 2 times s. So just like before, those s's cancel, and now we're left with the limit as s goes to infinity of s plus 1 over s plus 2. So if you try to plug in your infinity directly, we end up with infinity over infinity, and that's not an answer. That's not a number. That could be actually anywhere in the complex plane, from positive infinity to negative infinity, from positive complex infinity to negative complex infinity. So you can do L'Hopital's, which involves taking derivatives, right, top and bottom, but instead, because in electrical engineering our functions are much better behaved than mathematicians have to worry about, we can take a bunch of shortcuts. And I'll show you one of these shortcuts now. Just as an example, when I say you can just plug in the number over here, a mathematician would recoil in horror, because he or she would say, if you want to find out what this function is doing at 0, you absolutely can't plug in 0 because it will tell you this. And instead, the correct answer is the limit goes to 0 would be either positive infinity or negative infinity. But in electrical engineering, we don't have things like this. We have really well-behaved functions. So you can plug in a 0, and if it works, it works. And if you get an infinity answer, you got to do something else. Similarly, for finding out problems when you end up with infinity over infinity, rather than L'Hopital's rule, instead, just if infinity over infinity, just divide by s. So we're going to divide top by s, and when we divide the top by s, we get 1 over s. We'll divide the bottom by s, we get 1 over 2 over s. And now look, you can directly plug in, that was shouldn't have drawn the equal sign in there. And now you can just plug in your s equals infinity, and you get 1 plus 0 over 1 plus 0, which is 1, and very well defined. And that's faster than taking derivatives of top and bottoms.
So I have a question.
Shoot.
Explain the divide by s. Where did that come from?
Well, you can do anything to the top and bottom, right? I could have added 17 to the top and bottom, and I haven't changed.
Oh, okay. Gotcha. All right.
As long as I do the same operation to the top and bottom, I haven't changed anything. I could multiply the top and bottom by 17, which is multiplying by 17 over 17, which is 1. So we could divide them by s, we could add them by s. And I'm just telling you that the secret is to making, if you ever get this, then do that. And that will always make it work.
Gotcha.
In electrical engineering only, because our functions are so well behaved.
So, sir, I just have one question, just because I was a little behind taking notes.
Yeah.
The first example you gave, you said just set s equal to 0, right? That's how you get 1/2.
That's right.
Okay.
And if it works out, great. And if it doesn't, divide both sides, top and bottom, by s. For the second example, same thing. Just substitute in the infinity. If it works, great. If it doesn't, just divide top and bottom by s. What if it's still infinity over infinity after you divide top and bottom by s? What would you do?
Divide by s again.
Just divide by s again. So we've covered initial and final value theorems. Any questions on that?
Yes, sir. I got one.
Shoot.
So we did the final value theorem on the same problem as we did on the initial value theorem, but we got two different answers.
Right. Because this, if you were to take the inverse Laplace transform of this, you would end up with a function that looks like this. Starts off at 0. It's 0 for time less than 0. It begins at 1, and it decays down to 1/2. So therefore, our initial value theorem, what is it at f equals 0, is 1. And our final value theorem, what it is at infinity, is 1/2.
That makes sense. Thank
Mhm.